Yes. Hello, everyone. Welcome to MACSMIN, Mathematics and Computer Science for Materials Innovation. It's a great pleasure to introduce Professor Michele Ceriotti from EPFL in Switzerland, who will talk about an equivariant representation to learn long-distance interactions. Over to you, Michele, please.
Thank you, Vitaly. Thanks, everybody, for joining. I just want to give a little bit of background on what I do and what I'm trying to do, because I think I might be from a slightly different community. So the bottom line is that what we do is modeling matter, both molecules and bulk solids at the atomic scale. And as much as everywhere over the past few years, machine learning has arrived and is everywhere, and it's also entering into the basic tool chain for this kind of applications. And so if you want, a big distinction that I want to make, because as you will see, it will play an important role in the approach that we follow and the type of results that we are looking for. I make a very clear-cut distinction between machine learning models that aim to perform an end-to-end prediction, basically these being sort of black box models that take, for example, the chemical formula of a compound and try to directly predict the final property that you want to know about this molecule. It could be toxicity, or could be somehow the effect that this molecule has once you put it in the human body. And so what we are interested in doing is something which is much more close to a physical modeling of matter. And so the idea is that we go through a chain of modeling steps in which we describe a molecule as a collection of atoms. We compute properties for this collection of atoms, for example, the interatomic potential that tells us how that specific configuration is stable. Then we might want to do some statistical sampling to describe how this molecule behaves in a realistic setting of temperature conditions, and then we understand what is the mechanism by which this molecule has a certain effect on the human body. So basically the idea is to inject machine learning into this bottom-up modeling tool chain, and the most obvious place to inject machine learning in this tool chain is basically at the point in which you apply quantum mechanical calculations to predict the properties of a molecule. So typically, if you want to do this bottom-up modeling of matter, the most time-consuming step is to take the coordinates of the atoms, solve some approximate form of the Schrödinger equation, and extract properties for these individual configurations. And again, we might be speaking about the interatomic potential, but we might also be speaking about other properties, the dipole moment, charge density, the molecular Hamiltonian, and you name it. And basically the idea is that after having done a small number of these quantum calculations, we train a machine learning model to act as a surrogate model that allows us to predict the same property that you would compute by a quantum calculation with a data-driven model that is more time efficient. So just to give you an idea of the kind of things that you can do, because this is now something that is really part of the day-to-day routine of somebody who wants to model matter at the atomic scale. So you can, for example, compute optical properties, so how the infrared or Raman spectrum of an aqueous solution would look like, so that you can compare experiment with theory and understand the mechanisms that, where does a certain peak in the Raman spectrum come from. You can follow phase transitions in matter in extreme conditions. This is a series of phase transitions that occur in amorphous silicon under pressure. And we can also compute electronic properties of these configurations, and so we can also infer what would be the conductivity of this sample as it goes through this sequence of phase transitions. And this is important because this is how experimentally you know what's going on. As I mentioned, you can predict properties that go beyond just the stability, electronic structure, but also, for example, the dielectric tensor of a material. So you can, for example, study ferroelectrics. This is a depiction of the structural transitions that occur in barium titanate as you change the temperature. As you reduce the temperature, you go from a cubic paraelectric phase to a series of ferroelectric phases. And given that we also predict the polarizability and the polarization of these samples, we can also compute the temperature-dependent dielectric constant, which again is typically what you would measure experimentally and what you would care about in using these materials for applications. So when it comes to machine learning, also for these type of problems, there is a very strong tendency of making all-inclusive models. And I think that, ChatGPT is a good, very famous example of this. When you use ChatGPT, you are basically getting wholesale a model that involves the architecture of the model, how the model is trained, and also the training set that is used to determine that model. And so you basically get a package with everything has been chosen, and I compare these to, pre-mixed drinks. You get a Bacardi Breezer and, does its job, but you don't have really much freedom in choosing what you are getting. So the idea of what we have been trying to do over the past few years is trying to deconstruct these machine learning models, understanding what are the mathematical ingredients, how they relate to the physics that we are trying to model, so that eventually, you can guess where this is going, you can basically mix your own and get a model that is really adapted to the class of materials and the type of properties that you need to predict. So one of the directions in which we have tried to decline this program of understanding what goes into a machine learning model is trying to rationalize how you represent atomic structures when you want to use them as the input of a machine learning model. And I think that this might be something which sort of resonates with the kind of things that Vitali and other people in this community are interested in. So from a mathematical and sort of generic machine learning perspective, what we're dealing with is a description of atoms. So we describe a molecule or a material as the collection of the position of the atoms and labels that tells you whether you have carbon, oxygen, or hydrogen in a certain location. So this is basically a point cloud decorated with the nature of the elements. And an alternative way of looking at this type of geometric problem is to regard a molecule as a graph, but it's a geometric graph in which the edges are decorated with information on the relative position of the different atoms. Now, these two descriptions are really kind of equivalent, but
Michele,
of course, yeah.
Could I ask a question here?
Of course.
Since you mentioned molecules, so since, well, we are still learning chemistry, but we already understand that atoms and molecules have strong covalent bonds.
Yes.
At least neighboring atoms.
Yes.
However, many databases, real databases of molecules, for example, QM9, they contain data in the form indeed of a point cloud without this bond information.
Yes.
And also your picture here on the right shows, if I understand correctly, all all edges, so a complete graph on
Yes.
all atoms.
Yes.
So may I ask how, so when you work in practice, do you use only covalent bonds, or do you use all pairwise interactions?
This is an excellent question, and one that actually connects very directly to this notion of end-to-end models versus bottom-up modeling. So in an end-to-end model, typically you want to describe you want to describe ethanol as ethanol. You don't want to specify exactly where the atoms are. At that level, it's very common to describe the ethanol molecule as a graph, and that, as a discrete graph, not even decorated with geometric information. So it's just the adjacency matrix is 0 or 1, and that's it. And that makes sense if you want to predict the toxicity, because the toxicity is not the property of a specific arrangement of the atoms. It's an ensemble property, and actually is a property of the relationship of that molecule with a certain species, right? So the toxicity for a squirrel will be different from the toxicity for a human. So you cannot, it doesn't really make sense to achieve a full description of the geometry of a molecule. On the other hand, if you're trying to predict the results of a quantum calculation, what you want is a complete description of the geometry of that molecule. And from this perspective, it does make sense, the bonding, the covalent bonds are just an approximation. They are an abstraction that helps chemists interpret the behavior of a molecule. But from the point of view of quantum mechanics, given the position of the atoms and assuming a Born-Oppenheimer approximation, the bonds are something that you can learn from the position of the atoms. So shouldn't be part of the input. And this is why when we do this bottom-up modeling, we don't use information on the connectivity, but we use all the edges.
Okay, thank you, Michele.
So, as I was already mentioning, so what we do basically is really we take complete information on the geometry of the molecule and we try to predict the properties that are associated with this molecule. Now, given that we are not just dealing with a generic point cloud that describes an airplane or a chair, but we are describing atoms and molecules, there are some fundamental physical properties that should be fulfilled by this mapping between the point cloud and its properties. So, for example, at the quantum level, the properties of structure tend, in the vast majority of cases, they are smooth functions of the atomic coordinates. So you want the mapping between the structure and the properties to be differentiable and also have a certain degree of smoothness, in the sense that you can expect that the resolution that you need to learn is not infinitely sharp, which of course is very useful because it means that you can interpolate more effectively. An important requirement is that you want this mapping to be complete. So you want that if you have two geometries that are different, it should be possible to predict that the properties of these molecules are not the same. And what makes this requirement not so trivial is at the same time, it's very useful to make sure that the mapping is symmetric. And this is something which I think is you are extremely well familiar with. If you have a structure that is an FCC solid, you want that the description that you use when you're using the primitive cell or the conventional FCC cell or some type of supercell that is useful for a given application, you want these descriptions to map to exactly the same answer, because they are just the same structure seen in a different basis. And so one last requirement, which actually will be very important for the second part of this presentation, is that usually we try to build a description that is additive and is local. And this is because this local description is very useful to compress information. We want to incorporate information that we don't need to know about the relative position of atoms that are 50 meters apart, because their interaction will be negligible. And this, of course, simplifies machine learning, because it means that you only need to care about a finite number of degrees of freedom. So these physical requirements have an impact on the functional form that you use to describe your model. For example, if you want to incorporate additivity and locality in your model, you will typically write the property Y of a structure A in terms of a sum of the properties of atom-centered environments. So basically, we don't try to describe Y as a function of the coordinates of all the atoms, but we write an ansatz in which properties are decomposed into a sum of atomic contributions, and each atomic contribution only depends on a finite number of atoms centered on the atom I. Symmetry means that the functional form that we use should be invariant or covariant with respect, for example, to rotations. So if we have a vector, for example, the vectorial property for a structure that is being rotated by rotation R should just be the property of the non-rotated structure with the rotation applied to it. And similarly, we want to have a permutation symmetry with respect to the coordinates of the atoms. So now, once you enforce all of these requirements, this actually restricts quite substantially the design space of possible models, because basically it means that we are trying to expand the property of our structure in terms of properties of atomic environments, and we want to express these functions in terms of symmetric function of the coordinates of the atoms. And so basically the space in which we are trying to expand these properties is a space of symmetric polynomials centered that depend on the internal coordinates of your system. So basically, you might, for example, want to restrict, to approximate this property in terms of properties that only depend on pair of neighbors. And then you would have to symmetrize these by summing over all possible pairs of neighbors. So basically, we approximate the properties of an environment AI as something that depends on the coordinate of two of the neighbors. And then we sum over the indices of these two neighbors, and therefore we make the prediction independent on the order by which we provide the neighbors. And one important realization is that you can write these as a cluster sum, so as sum over pairs of atoms, but you can also write these as a histogram. Basically, this is just a rewriting of these in which we express this function as an integral of delta functions, that the delta distributions that identify the position of the two neighbors, together with a function that acts as weights. Essentially, this is a linear regression in the histogram of the neighbor positions. And the reason why this is useful is that rather than having to sum over the neighbors, over pairs of neighbors, now we can describe these in terms of neighbor densities, rho I. This is the density of neighbors around atom I, and we just need to take tensor products of this density. And so formally, the complexity of this calculation is only linear in the number of neighbors. If we had to evaluate these, we would have had a cost scaling quadratically with the number of neighbors. Now, formally at least, we need to compute this density, which the cost is linear, and then we take tensor product. And then, of course, in practice, you never do these integrals explicitly. These you can write in, if you're a physicist, you might be familiar, we are basically borrowing the Dirac notation to express the fact that this density can be expressed in real space, but can also be expressed onto any finite discrete basis, approximated at least on a finite discrete basis, and therefore you can write this integral as a sum over the coefficients of this expansion. So pictorially, what I'm saying is that you can describe your environment in terms of n-point correlations of the neighbor density. And then you could express these on a continuous basis, but also discretize it, and then you have a discrete problem, and the discrete problem that then you implement in terms of linear regression on a basis of local descriptors. So, of course, permutation symmetry is only one of the symmetries that we want to work with. And if you want to incorporate rotational symmetry in this framework, what you need to do is symmetrize the over rotations, the function that we are computing over the neighbor pairs, or equivalently symmetrize the density correlations over rotations. So basically, again, there is a sort of a duality between an expression for this property as a symmetrization of a generic function of the coordinates of two neighbors, or we can equivalently describe this as a symmetrized density correlation that we can then expand into any basis. And now, the advantage of picking a good basis then is that if we expand these densities in a basis of spherical harmonics, we can exploit the properties of SO3 to perform this integral analytically, and then we can express this prediction, this linear regression exercise in terms of basically the explicitly computed symmetric components of the density correlations that are basically a contraction over the m angular momentum number of the products of the expansion of these two densities. So if we do this again pictorially, we can express this as a symmetrized density correlation, even though in practice we would always compute these in terms of spherical harmonics coefficients, because then we can do very easily the projection of this tensor product onto the space that is invariant under rotations. So these can also be generalized to make equivariant predictions. Again, here the integrals get really, really nasty, but the concept is the same. So now we want to make a prediction that is equivariant. We need to project the density correlation onto the component that has the correct symmetry. So if we want to predict a vector, we need to project the density correlation over the L=1 spherical harmonics, basically, so that we have the same rotational behavior as a vector. And once again, if you express these in terms of density correlations, you can much more conveniently compute all of these on a basis of spherical harmonics. And now the selection rules to pick out the components with the correct angular momentum character in this case involve a sum with Clebsch-Gordon coefficients. So basically, in order to compute correlations, you need to apply the same physical rules that you apply to do the sum of angular momenta, which are just the combination, the product rules for SO3. And again, pictorially, we can represent these as tagging the density correlations with a component that singles out a specific spherical harmonics component. Yes.
Michele, could I ask here if you could repeat the property of full equivariance? So what's the difference between invariance and equivariance?
Invariance is just a special case of equivariance. Basically, equivariance basically is the notion that if you are trying to predict a property, and you, I mean, you are trying to compute a function, you apply a transformation to the arguments of this function. If the function is equivariant, then the result should be the same as the application of the symmetry operation to the result of that function. Now, if that function is invariant, then it means that basically the function is, I mean, for geometric transformations, the function is a scalar and should basically remain invariant under rotation. If it's a vector and you are considering rotations, it should transform like a vector. If it's a tensor of higher order, then you can decompose it in irreducible components that transform like spherical harmonics. And then basically your model should also transform like spherical harmonics.
For example, if you have, say, two specific atoms, so very unique atoms in a molecule, so a vector from one atom to another atom, so it's not invariant under rotations, but is it equivariant in this language?
Exactly, exactly. Basically, it would be covariant, and equivariance is just a general, you know, covariance carries a strong physical connotation of transformation under, you know, either rotation. If you're not doing relativity, typically covariance is how something transforms under rotation. So equivariance is just a general term to convey the notion that the result of a function transforms under the operation of the elements of a group in a way that is consistent with the application of the element of the group to the arguments of that function.
So these words, a fully equivariant framework.
Means that
what does it mean?
It means that no matter the type of property that I'm predicting, if I physically transform the input by permuting the entries of a matrix or rotating a molecule in space, the output also transforms in a way that is consistent with this transformation.
So it is indeed very different from invariance.
Invariance is a special case. Invariance is a special case for the case in which the property that you are predicting
remains constant.
Remains constant, yes.
Okay, thank you, Michele.
So, so basically, the message that I want to convey here is that you can express descriptors, pretty much every descriptor for the structure of a molecule or material as a projection of these density correlations in an appropriate basis. And this is basically because these density correlations form a complete basis for the symmetric polynomials. And now, depending on how many densities you include in the model, in the descriptor, you end up with different body-ordered approximations of your target. For example, if you include just one density and you symmetrize the density over rotations, you end up with something which is essentially the pair correlation function, so the histogram of pair distances. Now, this is a way of describing an atomic environment, but it's, of course, you might want to have a more a richer description, and for example, then you could go on to the symmetrized correlations of two densities, and this is equivalent to a description of the histogram of two distances and one angle within an environment. And this generalizes to histograms of tetrahedra, and then it becomes sort of pointless to give a name, but you are basically describing correlations between 3, 4, 5, 6 neighbors. And one important realization is that if you build linear models on top of these descriptors, no matter how you discretize them, what you're doing is basically expanding your property, for instance, the interatomic potential, as what is called, at least in our field, a body-ordered expansion. So basically you approximate a property of a group of atoms as a sum of pair terms, terms that depend on 3 atoms, terms that depend on 4 atoms, and so on and so forth. So there is really a one-to-one mapping between these descriptors and very well established way of expanding atomic properties in terms of a hierarchy of cluster terms. So this hierarchy can actually be computed quite efficiently, exploiting the fact that you can expand all of these, you can basically project all of these correlations on a irreducible basis of SO3. So basically the idea is that you start by expanding the neighbor density in radial functions and spherical harmonics, and then you have a rule to combine these correlations in a way that preserves the irreducible behavior with respect to the operations of O3. So essentially you take you start from a density expansion, and then you have a recursive formula that takes a component that transforms like an angular momentum KQ. You combine it with the expansion coefficient that transforms like LM. You use Clebsch-Gordon coefficients, and this guarantees that the result transforms like a spherical harmonics with angular momenta lambda and LZ component mu. Now, which of these components you should use depend on what are the symmetry properties of your target. So if you want to predict a scalar, you should keep only the components that are fully symmetric, and so basically this would be the S components, the L equals 0, M equals 0 components. But in order to build this hierarchy, you have to keep all the components as the intermediate steps. So even if at the end you want to learn only with the invariant part, your machine learning hierarchy should keep all of these intermediate angular momenta. Now, one problem, and something that, you know, I know that this is basically how Vitaly and I got to know each other, is understanding whether keeping just some of these correlations, and in particular keeping only the invariant terms in this hierarchy, is enough to fully characterize in a symmetric way a bunch of atoms. Now, it is very well known that keeping only distances is not enough. If you can basically take the set of distances between a group of atoms, and you can build different structures that have the same set of distances, but since you are not using, you are not specifying which atoms are connected by a certain distance, you can build two structures that are different but have the same set of distances. And something that we realized is that actually this is also true if you consider more complicated objects that contain collections of distances and angles, and there are also counterexamples for tetrahedra, and basically it is not clear at which point you can stop in this hierarchy if you basically want to only use the invariant components of the descriptor. So the reason why we care about these is that when you use these descriptors as the basis of a machine learning model, if the descriptors are not capable of differentiating two structures, no matter how sophisticated is your machine learning model, if you build it on top of these invariant descriptors, you will not be able to differentiate between the molecules. You will not be able to predict that the two molecules have different properties. basically, in this plot that I'm doing here, this is just a sort of a generic path in configuration space. And if two structures along this path seen through a certain set of invariant descriptors have exactly the same features, then whatever you do, the machine learning model will predict the same properties. And this is problematic because since we want the model to be smooth, the problem will also affect structures that are in the vicinity of these structures. So basically, as it often happens, you know, physicists, not to mention chemists and material scientists, like to ignore mathematical paradoxes, but actually when you get a pair of a construction that gives you some very weird structures that are problematic, usually this also translates into numerical instabilities for structures that are very, very reasonable. So we have been trying to work around this problem, and one way that we have found to go around this problem is to change the way we symmetrize the structures. So basically, our end goal is to have a description for an environment that is symmetric with respect to the permutation of the label of the neighbors and symmetric with respect to rotations. So this hierarchy of correlation functions is basically equivalent to taking histograms of tuples of neighbors. So we basically disregard all the information on the labels of the neighbors, and we make sure that we take only the part that is symmetric with respect to rotations. Now, we haven't been able to solve the problem of getting higher body order correlations that guarantee injectivity in this mapping. So instead, what we did is basically trying to make sure that the information is not lost upon symmetrization. And one way that we have found to solve this problem is to do only partial symmetrization. So rather than symmetrizing over the coordinates of all neighbors, we leave two neighbors out of the sum over neighbors. And by doing this, now it is sufficient to keep just one set of neighbors, and we have all the information that we need, because the two neighbors that we have selected, essentially, if they are non-collinear, they define a local coordinate system, and within this local coordinate system, having the histogram of the neighbors is enough to characterize the position of all the neighbors. Now, the problem that you have is that this description is invariant to rotations, because basically we pick only the invariant part of this correlation with two tagged neighbors, but it's not invariant with respect to the labels of these two neighbors. So one possible solution for this problem is to consider the whole ensemble of coordinate systems, apply a nonlinear transformation in this space that is still equivariant with respect to the label of these neighboring atoms. It is simple to actually build descriptors that are complete at this level. There is a whole bunch of universal approximations, and then only after we have applied this transformation, we sum over the neighbor pairs and obtain a description that is fully symmetric, invariant with respect to the labels of all the atoms, and is also capable of differentiating structures that otherwise would be indistinguishable. Basically, by doing this, we can differentiate structures that are degenerate with respect to the labels of all the that are degenerated to three-body correlations. But since we apply a nonlinear transformation in the middle, now we have descriptors that can differentiate between them. Okay, so this basically the end of the story here is that by deciding the point at which we apply a nonlinear transformation, we can guarantee that we have an injective description, even if we only deal with a finite order of correlations, which is very convenient because it avoids the exponential increase of complexity that you get when you take higher and higher orders of correlations. So if there are no questions up to this point, I want to briefly move on to discuss a problem that is not solved by these. And the problem, yes.
Michele, could I ask, so you claimed what injectivity or completeness of this new representation?
Yes.
So do you have a more formal theorem stated?
So
in the paper?
So this is discussed in the paper, but actually this relies on this deep set paper. So basically, so it's very well established fact that if you have that a certain family of neural networks in the limit of infinite depth, of course, these are always statements that are true in the appropriate limit.
I see. So it's an asymptotic result. So
exactly.
Okay, in the limit.
Yes, and so, but you know that you have a way of systematically making these more complete, and heuristically, this is much simpler than converging. These is much simpler than converging this body order expansion of the density correlations, basically.
Oh, okay, so could I ask maybe a related question? So,
yes.
Of course, our atoms are not ordered. However, in a simple case, when atoms are ordered, you probably agree that the distance matrix on ordered atoms is a complete invariant, right?
Yes.
So, okay, so now we have unordered atoms.
Yes.
But what if we take simply all m factorial permutations and consider m factorial distance matrices?
Yes, that would be perfectly fine, but you would have a factorial to deal with.
Yes, but so in the limit, so m factorial is a big number, but it is actually a finite number, right?
Yes.
So why not use with some factorial distance matrices?
Because we want something which is practically usable.
Okay.
At the end of the day, we are interested in using these. Sure. And so it's important to, so the point is finding a formulation that is practically usable, that basically converges fast enough that we can use it in practice.
Do you have complexity results saying that it's faster than, say, m factorial for a number of points?
No mathematically strong results. We have empirical evidence, but no strong mathematical result. I mean, I'm not a mathematician, so.
Yeah. Okay, thank you, Michele.
Cheers. So, but yeah, I wanted, I hope I just wanted to give a little bit of context for another problem that is not fully solved yet. And this basically has to do with another limit that you have to take, which is the limit of the size of these atomic environments, okay? Because essentially when you do this decomposition, when basically you describe your structure as a sum of atomic contributions, you assume that you can truncate these correlations at a given length scale. So the question is, how far do you have to go? And, you can try, and typically what you observe when you try to build a model and you try to truncate it at different distances, 2, 2.5, 3 angstrom, and you see how well your model can learn, you see that if you take a too aggressive truncation, your model will basically saturate. These are for learning the cohesive energy of molecules. And, for molecules, since they are so much dominated by the covalent bond, 2 angstrom is not too bad. But at a certain point, you need to describe hydrogen bonding. And basically, there is just no information there. And the problem is that, for covalent bonds and small molecules, you actually can get away with taking like a 5 angstrom cutoff and potentially combining models with different length scales to get some sort of multi-scale nature of the model. But the problem is that when you want to do this for a system that is dominated by electrostatics, it's basically hopeless because electrostatics is 1 over R, and it basically never converges. It's a conditionally convergent, the energy of an ionic crystal is a conditionally convergent series. So you get to a different result if you converge to the limit using cells of different shape. So there is no way we are ever going to be able to converge electrostatics by just taking larger and larger cutoffs.
Michele, does it mean that this electrostatic energy or potential, is it simply not yet mathematically defined? So
you can define it. It's just in the same way as you can you can pick a definition of the limit of a series, and then you have a well-defined limit also for series that are not conditionally convergent. In physical terms, what this means is that when you have a finite crystal, the total energy depends on the surface. So it depends on the termination. But also physically, there are effects that, if in practice, limit the range of electrostatic. You have screening, basically atoms react to the presence of an electric field. For example, if you have a metal, electrostatics is perfectly screened. The electrons move to compensate the electrostatic field, and so the electrostatic field outside of a conductor is 0. So in practice, there are both computational and physical ways to define this property, but these ways do not imply taking an actual limit of a finite cutoff. It just doesn't work.
Right. So for an infinite periodic crystal, there is no convergent series.
There is a convergent. I mean, you can choose a summation order that guarantees convergence.
Summation order. Yeah, because not all terms are strictly positive.
Exactly. It's conditionally convergent, and so you need to choose a convention to take the summation.
Yeah, and it depends on the order of atoms, say, in a unit cell.
Well, it depends on, in a way, yes.
Okay, thank you, Michele.
So basically, the solution that we are exploring to do this is to exploit the fact that there are solutions for this problem for electrostatics in the periodic systems, and these work by solving the electrostatic problem in reciprocal space. So we do the same to define descriptors that have the correct asymptotic behavior. Basically, we take the atom density, which is the same object that is behind these local descriptors. We solve the Poisson equation for this density to obtain a fictitious potential. This is not a physical electrostatic potential. It is the potential that would be generated by a distribution of charge corresponding to the position of the atoms. I emphasize that it is not physical because in order to incorporate information on composition, we use a different density and therefore a different potential for each atomic type. And then what we do is that we take this potential that we can compute in the Fourier domain, and we symmetrize it. And so we have local descriptors of this non-local quantity. And then we can compute correlation functions of this potential, correlation functions of this potential with the local density. And in particular, something which is very nice is that if you take the symmetrized correlation between the density and the electrostatic potential generated by the density, I don't think that I have the time to go through the whole details of the derivation, but you can look it up. Basically, you can find that formally these descriptors that you obtain by basically correlating the density and the fictitious potential built on the density describe the same type of physics that you have with multipole electrostatics. Basically, the electrostatic potential generated by the density encodes information on the far field distribution of the atoms and on the multipoles of this far field distribution. So then the model that you build is basically describing the local response, and the local response is described by the distribution of the atoms locally to the field generated by the atoms in the far field. And so this is very, very clear when you try to build models, for example, of the interactions between molecules. If you describe the interaction between water and carbon dioxide, you need to have information on the dipolar interaction generated by the water molecule and the quadrupolar interaction generated by the CO2 molecule that has, has no dipole because of its symmetry. And so this basically implies that you have to retain different angular momentum channels to be able to capture these different electrostatic terms. And so what is very nice is that at the end of the day, when you build a machine learning model on top of this, you still have enough flexibility to also describe different types of interactions. So even though we build this in a way that is really tailored to electrostatic interactions, the model has sufficient flexibility, for example, to also learn the interaction between apolar molecules, something like van der Waals interactions. And something that we are doing now is actually to generalize this idea, and rather than building models that are built on the electrostatic potential that you, as I mentioned, the way we do this in practice is that we Fourier transform the density, we solve the Poisson equation in reciprocal space, which is just dividing the density by k square, and then we back transform to have a real space object that we can localize. Well, you can do the same, and it's very simple to also build fields that have the correct asymptotic behavior to describe a 1 over p potential, or 1 over r to the p to potential. And by doing this, you can see that you can learn more efficiently different type of interactions. So for example, yes, you can learn interaction between apolar molecules, interactions that are driven by 1 over r to the 6 dispersion. But if you use a descriptor that has an intrinsic 1 over r to the 6 behavior, you are much more efficient than if you use a descriptor that has a 1 over r dependency. And so basically the idea here is really trying to incorporate the physics of long-range interactions into the mathematical form of these descriptors, which basically, again, is a different way of reaching this different type of limit, now the limit of including an infinite cutoff range. We incorporate these more efficiently by basically doing the machine learning in the Fourier domain. So to wrap up, probably there was a little bit too much content, but I wanted to give you an idea of how we are trying to incorporate some, okay, I wouldn't say rigorous mathematically, but rigorous in terms of physics, understanding of the ingredients of a machine learning model, both in terms of local interactions and also in terms of non-local long-range interactions that you can typically interpret in terms of 1 over r to the p asymptotic behavior. And so we really hope that by doing this, we will get better machine learning models and eventually we'll be able to do better predictions, and we very much hope that more mathematically well-versed people will be able to also put some of our heuristic results onto more sound mathematical grounds. And so with this, I'm finished. And if you want to learn more or also to see some of the code, here are a couple of references. So thank you for your attention.
Thank you very much, Michele. Please thank Michele physically, virtually. Let me stop the recording.